Here. We're continuing on, excuse me, continuing on chapter 12, and we'll wrap that up, and then we will roll into the last organic chapter, which is actually chapter 14. We skip 13, we'll come back to 13 afterwards because that's carbohydrates. So we're going to go from 12 to 14. The notes should be up there for you up on Canvas for that chapter as well. Okay, let's see here. A couple of things. So we've been talking about some more of these organic groups last time. We really got into a lot about, obviously, two important groups, and those were our aldehydes, which again has our functional group that looks like that, and our ketones, which again is really a 3-carbon run with that carbon-oxygen double bond there in the center. We talked about how to kind of go about naming these guys. Remember that our aldehydes get the AL treatment at the end in terms of your naming. Our ketones get the ONE, kind of like the name there, at the end. And a couple of important things about those functional groups that we talked about last time. Again, because of the sort of situation for our aldehyde here with that hydrogen at the end, that also means that that group always has to be at the end. So unlike a lot of organic groups, we don't need to give the location of that carbon-oxygen double bond. But in terms of numbering for other groups that may be there, it is always going to be carbon number 1. So again, we don't need to incorporate that number into the name for an aldehyde, but we do need to keep in mind that that is carbon number 1. Different though here with our sort of ketone is it will never be, as we talked about before, at the end. So it will usually need a number around 5 or more carbons, and about 5 or more carbons, you pretty much have some different locations as to where the carbon-oxygen double bond is located. So you do need to give the number for that guy in those situations, very much like what we've done with double bonds, triple bonds, the OH group in alcohols. And just like everything else, it does want to be sort of the priority in terms of the numbering. So we want to get that group the smallest number, whichever way that does it, left to right, right to left. And whichever way gives it the smallest number, everybody else obviously would be numbered accordingly, whichever way you kind of chose to go in that direction. We talked about some reactions that obviously involve these guys. We talked about how to produce really an aldehyde and also a ketone. And they really do kind of originate, if you kind of go back to the original, I guess you go way back to the original, it's an alkene. But basically, if we go from a primary alcohol, right, and we oxidize that primary alcohol, I'll spit that out, we do produce that aldehyde. And remember that that oxidation, as we talked about, is really the loss of H2, right, the 2 hydrogens. If we further oxidize our aldehyde, as we talked about last time, again, it will make us a new sort of organic group, which is a carboxylic acid. Again, that having the functional group of carbon-oxygen double bond, OH. And the difference, though, is in this oxidation, we are kind of adding oxygen. And again, the oxygen kind of, again, we talked about last time, there's a lot more steps involved, but the ultimate end result that occurs is basically we kind of substitute in there that oxygen that happens in this particular case. So really, you know, our aldehydes does come from a primary alcohol oxidation. We also talked about the idea of reduction, and we'll talk a little bit about it here again one more time, but reduction kind of heading in the opposite direction here is basically adding, you know, in this case, we're losing oxygen, takes us back to our aldehyde. Again, it has this as a functional group, again, losing the oxygen there. going this way through reduction, again, we're actually gaining back the H2, and that gets us back to our OH group, basically, that's there, like that. Those are the H's that basically come back as we go that way. This we also talked about was a secondary alcohol, right? And remember, a secondary alcohol would get us, if we oxidized it to a ketone, which again is our 3-carbon group. And if we try to oxidize that one more time, no deal, right? So no reaction going to occur in that case. Again, really because it's kind of missing a hydrogen that's essential to sort of the reaction that occurs. Obviously, reduction would go back this way. Here again, we're looking at the loss of H2 in this oxidation, gaining of H2 coming in this direction. So we talked about a couple of tests that will help you sort of determine whether you really started with the aldehyde or the ketone, and that was the Tollens test and the Benedict's test. They both are really oxidation tests where they are oxidizing agents, and basically they get reduced, but they will oxidize an aldehyde to a carboxylic acid. But if you treat a ketone with it, it will not do any type of reaction because it will not go through an oxidation reaction. So again, a negative test on one of those would imply that you probably started with a ketone if that was your 2 options. A positive test would imply that you started with an aldehyde. Any questions on some of that stuff we talked about last time there? Okay, so just kind of finishing up a few more sort of reactions and stuff here with our aldehydes. We sort of talked a little bit about it here just a second ago, but basically, you know, the oxidation and reduction reactions, they're really opposites of each other. They do occur sort of, you know, something is getting oxidized, something else is getting reduced. But in terms of the overall reaction, they're sort of the reverse reactions of each other. So aldehydes and ketones are reduced by sodium borohydride, RH2, mainly H2 we kind of deal with. The number of carbon-oxygen bonds is reduced. So we sort of talked about sort of the process by which we come back the other way. But for both an aldehyde or a ketone, it is really the important part of the structure is right here. And it's this guy right here, whether it be a hydrogen at the end or another carbon, that if you decided to do the reduction reaction, which again is H2, what's going to happen, and I think I might have went over this last time as well, but just to reiterate, what's really going to happen is the exact same reaction that happens when we talked about breaking a carbon-carbon double bond in an addition reaction with H2. Obviously, as we talked about before, right, there is no room for anybody to be added in at this point. So what always happens is the double bond becomes a single bond, and that essentially makes room for these guys to come in. And in the case of the H2, we obviously would be adding a hydrogen to opposite carbons, right? One hydrogen there, one hydrogen there. The exact same thing happens in an aldehyde or a ketone when you go through this sort of reduction reaction. The only difference is instead of a carbon-carbon double bond, that's going to become a single bond, it is the carbon-oxygen bond that's basically going to turn into a single bond. Everything else will remain exactly the same. And what will end up happening is, again, if we kind of follow this way, we basically will have the exact same bond, so whatever it is on either side, but we will make that double bond into a single bond. And the purpose of that is it now allows room, basically, at the oxygen and at the carbon to take one of these hydrogens on, one in each spot. And that's exactly what happens here is basically double bond becomes a single bond, and we put the hydrogen back on, and we put the hydrogen back on here. And that is, again, how we basically go back to our alcohol through the reduction reaction. And that's what we were just talking about right here, heading back to the left here. Again, breaking that double bond, making a single bond, adding a hydrogen to the oxygen, adding a hydrogen to the carbon. And again, it's basically the exact reverse reaction there of what we did. And that's what we see here. Here's our aldehyde. It is this part of the molecule that is going to basically change. And if I wanted to draw it going to the right, I would simply copy everything there exactly the same. Again, I would not change one thing except I made my double bond into a single bond. Adding that H2 means I will throw an H there and throw an H there. And now again, I have my alcohol over here. This platinum right here is a catalyst. It's just there to speed up the chemical reaction. It's not participating. It doesn't get put on anywhere. It's just there to facilitate it happening faster. That's my aldehyde on the left. My ketone on the right works exactly the same. Again, just going to draw it exactly like it is on the left, remembering that this is really the active part that's going to change, and going to turn double bond into a single bond. And now we're going to do the same thing, throw a hydrogen up there and a hydrogen there. And now we have our secondary alcohol, right? So we got our primary alcohol back this way and our secondary alcohol back that way. So again, the reduction, basically, if you want to think about it, kind of like the reverse reaction to our oxidation reaction. Any questions on that? All right, so why don't you take a second and figure out which structure should be the product here of what we got on the left, and we'll talk about it here in just a second. Good idea to try to figure out what you're starting with. Hopefully you could recognize this as a alcohol. Hopefully you could also recognize this as a secondary alcohol. Again, carbon there, attached to the carbon that has a OH. That is basically our secondary alcohol, which means we're basically taking a secondary alcohol and putting it through an oxidation, which means if you understand what you should get as a result of that is, we know before we even draw it, we really should get a ketone. And this oxidation means that the only part that's going to change in this case is we're going to lose hydrogen, which is right there and right there. Always on the oxygen, always on the carbon. Remember, those two guys basically come off and produce H2. The rest of this molecule, identical to what it started like. So without even thinking, I'm just going to really copy what's there. So I got that, I got that. I clearly am going to get rid of the two hydrogens that I took off. And now remember, when we take off two hydrogens, that makes this carbon short a bond. So we add our double bond in there and we get our ketone here, right? And our ketone is right there, the 3 carbon run with our double bond happening right there in the center. Any questions on that there? That looks like it is letter B. It looks like a winner. Yeah. Any questions on how to do that one there? All right, so
yeah. Sorry. So when we're writing it out, like on the test, like we have us write it out, we need the H2 plus. We need to have that the beginning part there first.
Yeah, so as I mentioned last time, technically it's there, but I think I might have mentioned last time. You know, I think I'd be happy if you just laid up that structure right there. You'd be probably okay. Technically, it is there. It's good to put it there. It also might help you understand. You know, you might not. It'll help you understand maybe not to put it back on that structure on the right. So just so you can see it's gone or something, it might help you to kind of do that. But again, I'd probably be more looking at the ketone that you drew.
Now, does it ever matter if the H2 is in the beginning or in the end?
It doesn't. So if you're asking, could I write the ketone plus H2, it doesn't matter. Again, as long as they're on the correct side of the arrow.
Okay, thank you.
You're welcome. Other questions? All right, so here we're starting with this alcohol here. We're doing a double oxidation here. So why don't you draw the products of both? So take it here through the first oxidation. The arrows are kind of messed up there, so let me just redraw it up here. H3C, CH2, CH2, OH. So first draw what the product would be here after that oxidation, and then whatever you get there, if you continue to oxidize it, draw the product of what you get there. So take a couple minutes to see what you come up with. Okay, so let's take a look at it. And again, sort of analyzing it before you maybe draw can sometimes help you, maybe point you in the right direction. Again, we should recognize this as an alcohol. We also should recognize this as a primary alcohol, which means that when we oxidize it, we should know we should end up with an aldehyde, which obviously has this group. And we know when we oxidize that, we'll end up with that carboxylic acid, as we talked about before. So I'm just going to redraw it down this way. And what I'm going to do is something here. What am I going to do? I'm going to do this move. I think I'm going to actually kind of draw out the last part there, just so we could kind of, again, see what's happening. So all I did is I drew out the CH2 here, and I drew out the OH, and I just put it on top. It doesn't really matter where you put it on that carbon. But what's going to happen is, obviously, when we go through an oxidation, we are going to lose that hydrogen. So remember, hydrogen coming off the oxygen, and you really can't choose either one of these hydrogens here. It doesn't really matter. They're both the same. So I'll just choose the one on the bottom. And remember, now we know that the rest of it really should be the same. And again, the H2 comes off. Everything else there going to be the same. Obviously, we're getting rid of those two hydrogens. And now, right, we know, oh, it's an aldehyde. I need to put in my double bond right there. And there's our aldehyde that's made. Any questions off of that one there? We also know that, as we talked about, as we then go through one more oxidation of this guy, we're actually going to, as we talked about, add oxygen right there. Again, we did talk about that. There's a lot more to it than just adding the oxygen, but for our purposes, basically an oxygen ends up there. Again, nothing else here on the entire molecule is going to change. It's just going to remain exactly the same. And we will end up with a OH here. Again, that is what has been sort of inserted through this oxidation process, remembering that there's three definitions of oxidation. The two that really apply to organic chemistry: the loss of hydrogen, the gaining of oxygen. So again, those are two distinct definitions of oxidation. Obviously, we come here from our primary alcohol to our aldehyde to our carboxylic acid. This is 1, 2, 3. This is 1 propanol, the alcohol. This is 1, 2, 3 propanal. This is, as we might have touched upon last time, 3 carbons, also based off of that propanoic acid. So again, you can see the names are also all related to each other as well. Any questions on any of those sort of steps there? Okay, so why don't you take a second here and see what you come up with. We're looking for two things here. We're looking for the product that you get when you take 2-propanol through an oxidation, and what is the product you get when you dehydrate, which basically means remove water from the 2-propanol. All right, take a second and see what you come up with in terms of what you would draw for each of those. All right, so let's see. Well, first off, obviously in this case, we got to start with our starting guy, which is 2-propanol. So again, remember, we want to work backwards in terms of the name. So OL tells us it is an alcohol. Propanol tells us it's 3 carbons. So that would be 3 carbons. 2 tells us the OH group is at carbon number 2. And the rest of it is hydrogens in this case. So this is, again, our 2-propanol, which is a secondary alcohol, which means right off the bat here, when we hit the oxidation of that guy, we should already know we should end up with a ketone, right, off the oxidation of that. So looking at part A here, I'm going to draw out the hydrogens and the OH group there on the carbon. Again, the oxidation of this guy going to be the removal of the H2, which are those two guys. Again, going to get us our H2 that will pop off basically. And again, nothing else here changes except that we hopefully know at this point we need to make a double bond there between these two guys to basically get to our ketone. We go from 2-propanol to propanone, O-N-E, right? Ketone. Any questions on that one? Now, B is a dehydration. So in B, we're going to be doing dehydration, which really means taking away water. So when we look at our 2-propanol, and what I'm going to do is actually just draw out everything. So again, we could kind of see what's going on. You don't necessarily have to do this, but again, it may just help you see things a little bit better. This is basically what we got kind of going on. Remember that when we put on the OH, it's basically being put on as water, right? It goes on as H and OH. If you also remember how it goes on is the OH goes to one carbon, the H goes to the other carbon, which means when it comes off in this process, we will take the OH off of obviously that carbon. Now we need to take an H off of a carbon next to it. In this case, there is 1, 2, 3 H's. In this case over here, 1, 2, and 3 H's. So remember that if there was an option for 2 carbons like what we have here, and one of the carbons had a lower number of hydrogens, you would take off the one from the smaller hydrogens. But in this case, they're both the same, take it off either way. We'll take it off there, and we'll take it off there. And that's going to form our water on this side over here, H2O. Everything else remains the same here, so absolutely nothing else changes other than we should take out the water. And what should we do in place of where we took out the water? We need to make sure carbon has the right number of bonds, so we lay up a double bond there between the 2 carbons that lost the water. And the reason why it doesn't matter in this case is if you double bonded to the left or you double bonded to the right, this is basically propene. There's only one spot for that double bond to go. So we go from, again, an alcohol here to an alkene. Any questions on that reaction there? Are those 2 reactions?
Professor, I do have a question. You can go back.
Yeah.
So carbon right here in the middle, where is the alkene? Is that just only has 6 bonds?
I think, you know what, I missed the hydrogen originally, so that was my bad. There should be a hydrogen right here if that's what you're asking.
Oh yeah. Okay.
Actually, I missed it. I had it up here. I missed it when I drew it down here. So there should be a hydrogen there. Thank you. And now everybody's got the right number of bonds. Thank you. That guy should. And again, that guy doesn't. Nothing happens with that guy. I just forgot to draw him on both of those guys.
Okay. Thank you.
You're welcome. Other questions on that? Okay. So write the structure and name the organic product when each of these is mixed with a Tollens reagent. So let's talk about each of these and sort of, first off, figure out, does a reaction take place? So in this particular case, the Tollens test is what we use to determine if we have an aldehyde or a ketone, right? And we know from just our conversations here, the guy that goes through oxidations to that carboxylic acid is the aldehyde. Again, the ketone will not, which means we could just basically look at the name here and go, that is butanal, which means yes, it will go through a reaction. Butanol is 4 carbons. Al means it's an aldehyde at the end there. So this starts looking like this. It goes through the oxidation here. And again, what that means in this case is we're going to actually just place in there our oxygen. And we would end up with this as our product, with that oxygen that's been inserted. As we talked about, that group right there is the functional group for our carboxylic acid. And naming wise, it does follow. So this is butanal. This, as you might imagine, would become butanoic acid. So it's how we kind of name our carboxylic acid, OIC, and then acid at the end of it. Any questions on that one? All right. Acetaldehyde is a kind of common name. It's also known as ethanol. Ethanol is a little bit easier for us to remember perhaps how to draw it. Ethanol means 2 carbons. Al means it has the aldehyde group there. So it looks something like this. When this guy goes through the oxidation here, again, what's going to happen right there is our oxygen. It will go through that because it is a aldehyde. And again, nothing's going to change other than inserting that oxygen right there to our carboxylic acid group right there. Carboxylic acid based off of 2 carbons. Ethane becomes ethanoic acid, OIC acid in this case. Any question on those two? Ethyl methyl ketone. Well, first off, we know it's a ketone, so right away, no reaction is going to really happen. This is a common name for a ketone. So again, that's kind of like what we did with ethers. Common name means carbon-oxygen double bond. On one side is a ethyl group, which is a 2 carbon group. Other side is a methyl group, which is a 1 carbon group. And then we put in our hydrogens. And there you go. Ethyl methyl ketone, also known as 1, 2, 3, 4 carbons. Butanone, right? It's the IUPAC name of it. Again, when we would go to oxidize this guy, as we talked about, no reaction with the Tollens reagent, as it will not go through oxidation. Any questions on any of those there? All right. So I want to talk about 2 other reactions that aldehydes and ketones undergo and sort of what's made as a result of those. So we're just going to kind of add those here to our little list here of reactions. This is a concept map from your book of everything we just talked about pretty much in this chapter. But I did want to talk, it's kind of the same, excuse me, it's kind of the same reaction we've been talking about, which is really what is sometimes referred to as an addition reaction with our aldehydes and ketones. And how these reactions occur is pretty much the same way as other ones. It's all about the carbon-oxygen double bond. Basically, we're going to make it into a single bond. It's going to allow some room for things to attach and so forth. So I want to talk about what happens when we take an aldehyde and we add an alcohol to it. So we'll start with what happens when we add 1 alcohol to an aldehyde. So we'll just use the same one we just looked at there, which was this guy. And let's say we want to add methanol to it. So I'll just draw it this way here. So we want to add basically methanol to this. And a couple of things here. Basically, when we add this, what we're going to look at the methanol as kind of 2 things. And the 2 things in this case are going to be this oxygen carbon part and the other guy is going to be the hydrogen part. So these are really the two parts that are going to be added in when we kind of do this reaction. So if we take this aldehyde and we take the one alcohol, what we will get is basically this thing will open up like this. It's going to make a single bond. So absolutely nothing here will change other than we're going to make a single bond there. And the purpose of making that single bond, right, is to basically open it up and allow things to basically add in. And if we do that, what we will end up getting in sort of this first round, if you will, is a couple of things. When we look at this guy, this part that I made in green is really negative. This guy will be kind of like positive. When this double bond goes away, it makes the bottom carbon more positive, makes the top oxygen more negative. And that's important for where things sort of end up. Opposites attract. And what that means is what's going to happen is the positive hydrogen there will be kind of attracted to the oxygen, and it's going to go over there. The negative oxygen carbon part is going to be attracted to the positive carbon that's on the bottom there, and it's going to find itself wanting to go over here. And what we end up getting is that oxygen carbon group attaching to the carbon, and we get the hydrogen attaching to the oxygen, making like an OH group. Any questions on sort of what's happening there? So kind of a similar thing that's happening, except we got a little bit bigger groups coming in. What we just made right there has actually a special name, and the special name of this sort of compound that we made, not really the actual name of what it is. This is what is referred to as a hemiacetal. So let's think about that name, hemiacetal. Acetal because it comes from a aldehyde. Hemi basically means it has the OH group here. So what are the important parts of a hemiacetal? The important parts of a hemiacetal, or how you could recognize it, is it will have a OH group, it will have a hydrogen, and it will have an oxygen carbon group. So those three things that I just highlighted is essentially what makes this compound what is referred to as a hemiacetal. Any questions on that there? Now, usually in a lot of cases, when we add this alcohol to this aldehyde, we sometimes add not one alcohol, but we actually add two alcohols. So what's going to happen is after we add the first alcohol, we will make this hemiacetal. Then what will happen is the hemiacetal will react with a second alcohol. So I'm just going to redraw my hemiacetal here. And what's going to happen is we're going to once again react it with perhaps the same alcohol here. So this is like our second alcohol. Now, in this particular case, what's going to happen is a couple of things, but there's a couple of ways you could look at it. You will see that basically we are going to take off water. So water is going to come out, H2O. And you may be wondering, where does the water come from? Again, through a process that is not of importance to us how it actually occurs, but we can just make water from these two guys. That's an O and an H, and this guy is a H, right? That's like OH minus and H plus. Those two guys are going to come and make water, right? So what does that leave us? It leaves us our original guy exactly the way it was, except that obviously we lost that OH. And then again leaves us that carbon, which if you remember, that carbon is kind of positive. And what else is left off of that alcohol? It is that negative part, right? So it's that kind of negative part that we were talking about above. This part right here. And that negative part is basically going to come in and replace where the water was and attach to it. And when it does, we will get this guy over here. That basically, if I get the right thing the right way, there we go. Basically, we'll add that OCH3 part in its place. Question on that there. Now, what I just made here, kind of the right color blue, sort of, is another important sort of type of compound. This is what is known as a acetal. What is the difference between the acetal and the hemiacetal? The difference is when we look at the hemiacetal, hemi you could think of means OH is involved. So there is no OHs here. What makes something a acetal is the two oxygen carbon groups. These two oxygen carbon groups and this hydrogen makes it a acetal. So when you take an aldehyde and you add just one alcohol to it, you stop right here at the hemiacetal. If you take that same alcohol, I'm saying that same aldehyde, and you add two alcohols to it, it takes you all the way to this acetal. So hemiacetal has OH in it. Acetal has two oxygen carbon groups. Any questions on that reaction there? Okay. Now, ketones actually do pretty identical thing. They do a pretty identical reaction to what we just looked at here. So let's just look at an example of a ketone basically going through the exact same reaction. So what happens when we take a ketone and an alcohol? So let's just take our ketone and we'll do kind of the same ketone here. 3-carbon guy. So we have our ketone and let's just add an alcohol to it. And again, it doesn't matter sort of how many carbons there is. So when we take our alcohol here and we take our ketone, same deal is going to happen. It's all about right there. And what's going to happen is that guy is going to break and make a single bond, just like the aldehyde did, just like a lot of things do. And that is going to allow for our addition of our alcohol. The alcohol will come on just like it did on the other guy. This part with the oxygen. Again, you could think of that part as the negative part. And the hydrogen is the other thing that will be added on. And you can think of the hydrogen really as, again, the positive part there. And they're going to end up in the same spot. Again, the oxygen more negative, carbon more positive, which means we will end up with our H over here and our oxygen carbon group right there added in. And again, just the color code for you, H there. And oxygen carbon here. This, as you can imagine, has a name very much like the other one. Some people still call it a hemiacetal, but some people call this guy really a hemiketal. It is a hemi, again, because it has that OH group. It's a ketal because really it started from a ketone. What is the difference between this and our hemiacetal? It's actually this guy right here. The hemiacetal, because it started from an aldehyde, has that H. The hemiketal, no H, right? Basically a carbon group here. Any questions on that one there? So what makes a hemiketal is an OH group, an oxygen carbon group, and no hydrogen there. Another carbon is basically there. And the same thing will happen is if you take two alcohols. So again, this, much like the last one, is what happens after the first alcohol is added. If we add a second alcohol, our guy there, our hemiketal, will continue to go. And what we will end up with, again, is something very similar to what we talked about with the other one. And here, adding our second alcohol. What happened on the last time when we added the second alcohol, we took off water. Same thing happens. We're going to take the OH from there and the H from there. That is going to get us our water. And what's left is this guy right here will stay pretty much identical to what it looks like before. Nothing going to change. We'll have that oxygen group over here. And now that leaves room for the remaining piece to come in, just like it did on the previous one. This guy, which is technically negative, will now find its way and come in to our carbon there. And it will add up on top there, and we will end up with a second oxygen carbon group. And as you might imagine what the name of this guy is, it is a ketal. And what does it have that's similar to a acetal? It has two oxygen carbon groups, but no hydrogen. So same thing, no hydrogen there because it comes from a ketone. So if you take an alcohol, one alcohol, and you add it to a ketone, you get a hemiketal, which is the structure up on top, right? If you add two alcohols to that ketone, you end up actually getting a ketal all the way through, no OH group present. Any questions on that there? So if we look at a couple of structures, those are the things you want to look at when you're trying to maybe identify one as being a ketal, hemiacetal, hemiketal, whatever it may be. So for example, if I had this structure here and I was looking at it, and I had this structure here, and I want to know, is this a hemiacetal, a acetal, a hemiketal, or a ketal? So try to correctly identify each of these structures here, the one on top and the one on the bottom, and see what you come up with. What is each of these? Look for those parts we just talked about, and we'll double check here in a second. Okay, let's take a look and see. So first off, it's always really about the carbon that has like an oxygen carbon type group or an OH group. So it's really this carbon. And what we see attached to this carbon are a couple of things. We see an oxygen carbon group, we see an OH, and we see an H that's attached there. So those three things actually tell us a lot. Let's start with the H. The H tells us that it came from an aldehyde, which means we're in the acetal range, which means it's got to be one of these two things. We definitely have an oxygen carbon, which might not be a lot of help to us, but we do see an OH there. Remember, the OH is the guys that are hemi, which means that this guy would be a hemiacetal because of that. Any questions on that there? Now, if we look at our bottom one, again, looking at the carbon that has all the stuff attached to it, really, we actually see 2 oxygen carbon groups. And we see when we look over here, no hydrogen attached to that carbon. So no hydrogen attached. The no hydrogen attached tells us that this guy originated as a ketone. And when we look around, we don't see any OHs. By the way, since it is a ketone, it means one of these guys. We don't see any OHs, which eliminates this guy, which means we've added really 2 alcohols here, and this guy would be a ketone. Any questions on that? By the way, how could I just quickly determine, what alcohol I added? Well, it would really be this part right here, right? And this part is really coming from the alcohol, which means if you just draw out that part and then turn it into an alcohol because it lost the hydrogen, it would be ethanol that came in there and was added to this ketone. You could also take away those parts and just take the middle part there, and you can pretty easily reconstruct the ketone that you started with, which is that middle part. You could do the same thing up here. This right here came from the alcohol, which means if I just drop that part out and turn it into an alcohol, I see that the alcohol I added up on top was actually methanol. I know this is an aldehyde, which means I pretty much can just run straight across here and take out the middle part. And turn it into an aldehyde, and I would have my aldehyde that I started with, which would be propanol. So you could actually deconstruct the structure there to get back really all the parts that kind of made it up. Any questions on hemiacetals, acetals, ketals? Obviously, you should be able to kind of draw those and also identify if they are, again, the hemiacetal, ketal. I think I wrote ketone twice. So this is a ketal, just to be sure. There you go. And be able to identify them. Any questions on any of the stuff from this chapter? This should wrap up this chapter here, which is chapter 12. This is the last chapter that was going to be on our exam, which is 1 week from today, I believe. So 1 week from today, again, we'll take the exam, which covers organic and inorganic stuff. So again, remember there's solutions and acid and bases, which involve calculations and a calculator. And then obviously there's the organic stuff, which you don't need a calculator for, right? So no big surprise on the organic stuff. You should probably be drawing these formulas, naming these things, drawing the results of these reactions, so there's not a big surprise as to what's going on probably there, functional groups and so forth. Obviously, the other ones will have some calculations. Any questions on any of that stuff there? Okay, then we're going to actually, like I was mentioning earlier at the start, we're going to leapfrog 13 for the time being, and we're going to kind of finish up our conversation about organic chemistry, which will take us to chapter 14 if I get there. I keep clicking, maybe it'll come. Maybe, there it is, chapter 14, which is pretty much the remainder of the organic groups. So again, a reminder that here at chapter 14, not on exam 3. Okay, on the final, obviously, but not on exam 3. So we are going to go back, like I said, to 13, but I don't know why in this edition of the book sheet through 14, which is organic after carbohydrates. They usually come the opposite way, but we'll go with it. So we're going to talk about carboxylic acids. We're going to talk about esters. We obviously talked a little bit about carboxylic acids. We definitely know, right, how it's made for sure. And again, we've been talking about it for the last couple of days, but really this is our starting from our primary alcohol that gets oxidized to our aldehyde, as we've been talking about, that gets oxidized to our carboxylic acid. So the carboxylic acid has the functional group of carbon-oxygen double bond and that OH group. So this is the functional group for carboxylic acid. In just formulas, it sometimes is abbreviated COOH. So again, like acetic acid is something that maybe you've seen before. It's abbreviated like that. It is a carboxylic acid, actually. If you drew it out, acetic acid, which is basically vinegar, it looks like this. And this is our carboxylic acid here. This is also 2 carbons, which is based off of ethane. And it's right there, actually. It is ethanoic acid. So how we go about naming carboxylic acids is, we kind of put OIC acid at the end. So ethane, you could try and drop the last part of it, the E, and put OIC acid is a way that we kind of name these guys. Or put IC acid after the alcohol name if you want. But that's basically how we get there. This is ethanoic acid, which is also acetic acid, and that's one that you kind of should know the common name. Acetic acid is used a lot, I would say probably more than ethanoic acid. And again, sometimes people call it vinegar. Propanoic acid, again, in our sort of line structure way here, that carboxylic acid group will be at the end. So much like our aldehyde group, this group will always be at the end. And here, as you can imagine, that is our carboxylic acid group. That's a benzene ring, which is how we get to benzoic acid, OIC acid there at the end. So as I mentioned before, in terms of naming, we do basically drop the OIC, we drop the E and put OIC. Because the carboxylic acid group is always going to be at the end, like our aldehyde, we do not need to lay up a number for that carbon-oxygen double bond. So, if we had something, say, like this. Let's stop there since I'm running out of room. Put some hydrogens in there, perhaps. We would count the carbons here. We would have 1, 2, 3, 4, 5, 6, 7 I drew. 7 is based off of heptane. We see our carboxylic acid group over here at the end. It becomes heptanoic acid. Again, this always is going to be at the end, which means in terms of numbering, it will get the priority, which means that this would be carbon 1, although we don't need to put that in the name, but we do need to use it for our numbering. That's 1, which makes this 2, 3, 4, 5, 6, and 7, which is important for any group that may be there. And in this case, the group would have to have a number of 6 because of that. So this would be 6-bromol heptanoic acid. Any questions on that name there? Okay. So here's a couple of other ones that we see here. Again, looking at our carboxylic acid group, which is at the end there, which is right here, and counting the carbons, which they nicely did for us, 1, 2, 3, and 4. 4 based off of butane. Drop the E, butane becomes butanoic acid. Again, no need to give the location of that carbon-oxygen double bond, but as you can see here, it is carbon number 1, which means our methyl group would be at carbon number 3, and we have 3-methyl butanoic acid. Any questions on that? Now, looking at the guy on the right, it is a little bit different in terms of the carboxylic acid on our sort of benzene ring, if you will. It actually is kind of off with the ring if you look at it. It's not incorporated into the ring. So the group itself is actually kind of bonded to the ring. And even though it is like that, that is obviously still going to make it a carboxylic acid because of this group. We also have the benzene ring, and that really is where we get the back part of our name here, which is benzoic acid, again, based off of benzene. When we get to the ring, wherever that functional group is attached, this will be carbon number 1 for the ring, which means that's carbon number 2 and carbon number 3. Going clockwise here will give us the smaller numbers. If we went counterclockwise, 2, 3, 4, 5 would obviously be a larger number if we kind of went in the counterclockwise way. We have 2 groups attached, which is dichloryl, which is where that part is, and they're at location number 2 and number 3 on the benzene ring. Any questions on that there? Here's just some names and some common names that are sometimes used a lot. Here's 1 carbon, which is methanoic acid, IUPAC name. 2 carbons are ethanoic. 3 carbons are propanoic, butanoic acid. Again, our line structures for them. Here's our IUPAC name, which is the way you probably should name it. And I probably would say out of these 4 names, these 2 names do pop up in common names a lot. So these 2 guys. So probably a recognition that these 2 guys are methanoic acid and ethanoic acid is probably a good thing because, again, people very commonly, I very rarely hear people say ethanoic acid when they're talking about acetic acid. So very, very rarely you see that. You should, though, probably name it as ethanoic acid in this class, but in sort of real life, if you will, with quotes, most people will probably roll with the acetic acid. Heck, most people will probably roll with it's like vinegar. So even though, it's a little bit more in vinegar than just acetic acid, but it is the primary sort of guy that's in vinegar. Again, formic acid, which is really methanoic acid. As you can see there from a red ant sting, that does not seem good. Irritates your skin. Sour taste of vinegar, again, is that ethanoic acid. And it really is sort of the major sort of contributor in vinegar as to what's there. All right, so why don't you take a second here and write the name for this guy and see what you come up with. So looking at this, remember, pretty much in all organic, we're looking for the longest continuous carbon chain. Remember, it does need to have the functional group, and our functional group is right here, right? That's our carboxylic acid group right there. Again, that's a carbon here, right? In line structure, we don't draw the carbon, but that's a carbon-oxygen double bond with the OH. So it does need to contain that group, which means if we start counting, probably like 1, 2, going up, 3, 4, and 5 carbons coming this way. We could go here and then down 1 more, but that's only 3, so that's less, right? So we're looking for the longest. So this run of 1, 2, 3, 4, and 5 carbons is going to give us the base of our name, which is based off of pentane. We see it's a carboxylic acid group, so that is going to be pentanoic, OIC acid. Again, no need to give the location of this because it's got to be at the end. But this will be carbon number 1 for numbering purposes, which means this guy right here would be carbon 2, that would be carbon 3, that would be carbon 4, and that would be carbon 5. That's important because remember, it is not just a lonely line hanging off there. But remember, at the end of that line really is a carbon, which means it also needs 3 hydrogens, which means a lonely line like that in line structure is really a methyl group, right? And we now know it's at carbon number 2. And putting all that together would be 2 methyl, I'll stretch them together, 2 methyl pentanoic acid. I spaced it a little much there, I think. Bring it in a little bit. Any questions on that name there? So 2 methyl pentanoic acid would be the name of this structure. Any questions on that? Okay. Then try these two here. Let's give the IUPAC names for each of these guys and see what you come up with. Okay, let's take a look here and see how we're doing. Let's see here. Got some names coming in, so let's see how we're doing. Again, obviously, we see on both of these, hopefully, and again, this is why it's important to be able to recognize functional groups. So it really does make other parts of your process here easier. We obviously see both of these cases here are carboxylic acid. So we do know that it's a carboxylic acid. It then should end in OIC acid. So we just got to work on, longest carbon chain that has that part of it. Again, here in the first case, you actually have a couple of options. You could go straight across, 1, 2, and 3. You could go straight across and up, which would also give you 3. And it honestly doesn't matter which way you choose. Again, I'm just going to go with the straightest. Sometimes it's just easier to see everything else that's sort of happening. So we'll go with the straightest in this case. And again, if you went up instead of straight there at this junction, it should come out the same. 3 carbons is based off of propane. Again, understanding that it's a carboxylic acid, would know how to change propane into propanoic acid. Again, because of this guy having to be at the end, we don't need to give the number, but this definitely will be carbon 1 in our case. This would be carbon 2. This would be carbon 3, meaning that our nice methyl group over here is going to be at carbon number 2, and try to squeeze it in better than I did last time, 2-methyl propanoic acid. Any questions on that one there? Okay, looking to the guy to the right, we're going to take the same sort of approach. We got our carboxylic acid group. We definitely know our name should end that way. We actually see that the longest carbon chain here is the entire benzene ring right here, right? So this is our longest carbon chain. Let me find coloring, so let me color that in. That is a benzene ring. It's a carboxylic acid. That gives us the base of benzoic acid. And remember that even though it's sort of off the ring here, where it attaches in should be carbon 1. We now could go clockwise or counterclockwise. If we go counterclockwise, it would be 2, 3, 4, 5. Obviously, if we go clockwise, 1, 2, and 3, that seems much better. 3-bromo benzoic acid. Any question on those names there? It is it is when it is a benzene ring, so it has to be a benzene ring here. So remember, there is a difference, say, between that guy and this guy, or the guy with the circle. Basically, it's the same thing. Again, this is benzene, and this is cyclohexane. So when we're talking about benzoic acid, it's basically based off of the name benzene. So it has to be a benzene ring for it to be benzoic acid. Other questions on that? Okay, so why don't you draw the structure here? Let me give you another one to draw as well. Why don't we do as well? Let's do 4-bromo 2-methyl pentanoic acid. And let's do 3,3 diethyl 3,3 diethyl butanoic acid. All right, draw those 3 guys, see what you want. If you want, you could draw the condensed structure if you want, or you could draw the line, either way. we'll look at both maybe. Okay, so since we're getting in, let's take a look here. And again, whenever we get the name, no matter what it is, sort of an organic, we just want to work backward. We get a lot of information here. Oic acid tells us it's obviously a carboxylic acid. They all end the same way here, which definitely tells us, again, the importance of knowing the functional group means that's something I should incorporate into my picture. Hexane part here tells us that it is 6 carbons. So again, much like anything else, you could just start with the 6 carbons. If I counted right, that looks like 6. Remember that it is the carboxylic acid group, which means it's got to be at the end. So since you're drawing, you could put it on the left-hand side or you could put it on the right-hand side. I'm going to put that group on the right-hand side. And the process of doing that means that this guy definitely will be carbon number 1 for me over at that end. And that's important because the rest of it is 4 chloral, which means I need to head over 4 carbons. So that'll be 2, 3, and 4 and put a chlorine. Everything else going to be hydrogens here, so that's going to be H2. This guy needs a couple. It has 2 lines. This one only needs 1, as there's 3 lines coming in. This guy needs 2, and this guy needs 3. Any questions on that? Now that you have maybe that structure drawn, it might be easier for you if you wanted to do the line structure. We would kind of do the same thing. We would do 6. So you want to start with 6 carbons, 1, 2, 3, 4, 5, and 1 more makes 6. And a little bit high on that side. We need to add our carboxylic acid group just like we did before. So I will do it over here at the end carbon. That again would make this guy carbon number 1, which would make that carbon 2, that carbon 3, carbon 4, carbon 5, and carbon 6 going that way. Just like before, we would go to carbon number 4 and put our Cl. And because it's a line structure, we would be done. You can erase the numbers if you want, but that would be what it would look like. Any questions on that there? Working backwards on this guy, we see the same thing, oic acid. We see basically pentane, which means we would do 5 carbons in this case. Going to put my carboxylic acid group on the right-hand side. Again, your personal preference. If you want to put it on the other side, you can, because I did that. That's going to be carbon number 1. Important for my 2-methyl here, which would be actually right next door, would be carbon number 2. Also important for my 4-bromol, which would be 2, 3, 4. Everybody else here going to be hydrogens. We need 1, 2, 3, 1 hydrogen. This guy needs 2, this guy needs 1, and this guy would need 3. If we were going to line structure this guy, we would start with the base of 5. That should be 5. 1, 2, 3, 4, 5. Again, I'm going to put my carboxylic acid group at the end, which makes that carbon 1. This again would be carbon 2, 3, 4, and 5. So carbon number 2 right next door would be a methyl group. I'm going to erase my numbers there. It's a little messy. There we go. So remember, in line structure, it really is just a line. Nothing at the end of it implies a methyl group. At carbon number 4, again, I'll get rid of my number there. It's just not in the way. It's going to be our bromine group. Here, because it's a bromine group, we do need to write Br at the end. That way we know it's not a methyl group, and that is our line structure for that particular one right there. Any questions on that one? And lastly here, looking at butanoic acid. So that is 4 for butane. Takes care of that. Going to make our carboxylic acid group at the end. That makes carbon number 1's there. We have 3,3-diethyl. So 1, 2, 3. Ethyl is a 2-carbon group. And diethyl means there's actually 2 of them. And they're both located at carbon 3. One at 1, 3, and one at the other 3. Takes care of both of those. Putting in our hydrogens. This guy actually doesn't need any. And 1 there. And if we line structure that guy, we've got 4 carbons, really. 1, 2, 3, and 4. Putting our carboxylic acid group at the end, carbon 1, carbon 2, carbon 3 will be 1, 2, and oops, if I don't hit the wrong button there, something like that. So that would be 1 carbon and 2 carbons going that way, 1 carbon and 2 carbons going that way, and our base of 1, 2, 3, and 4 carbons going that way. Any questions on that? Questions on how to name carboxylic acids or draw carboxylic acids? Okay,